To record this session as well. Yeah, Mark is typing. Okay. Uh, he's not typing anymore. So, welcome to the new session. This session, we are going to talk about several things uh, like linearization and bifurcation types, and solving some practice sheets questions, and drawing some bifurcation diagrams. But about Fitts-Nagomo model, neuron model, we don't do that this session because it is about two-dimensional systems, which Professor Pipa lectured. Therefore, first we need to talk about 2D sessions, and then we talk about Fitts-Nagomo neuron model. So next session we talk about that. But this session we also have an interesting paper which I will refer to. So let's go to the practice sheet here. So we talked about this potential, right? Last session. And now we want to talk about linearization. Why linearization? Because we want to investigate on bifurcation, and for bifurcation we need some mathematical tools called linearization. Here you can see that, for instance, we have two major things. One is that the way that we find fixed points, and probably you all know, and the way that we can find whether that fixed point is stable or not, whether it is stable or unstable. So the first example is this, that x dot is equal to x times 1 minus x. So if we want to say how to find the fixed point, we just say that x dot is equal to 0. Why? Because then it will be, there is no change in x, therefore it is a fixed point. So we just say that this x dot is equal to 0, and then we take the first derivative of it. And so about this, you can see that x is equal to 0 and x equal to 1, they are the fixed points, and the first derivative of it will be 1 minus 2x, and f prime at this 0 and this 1 tell you 1 and minus 1, and if it is positive, then it is unstable fixed point, and if it is negative, then it is stable fixed point, right? You can also talk about this example, which x dot is equal to 1 minus e to the power minus x2. And again, we just put it equal to 0, and you see that you can take this minus e to the power minus x squared to the other side, and then take the ln, and ln will kind of cancel out the exponential function, and ln of 1 is also equal to 0, therefore minus x2 is equal to 0, and therefore x equal to 0 is the fixed point. So again, for finding the stability, we take the first derivative, f prime of our fixed point, f prime of x. Actually, f prime of x will be like this one is going to be 0, and this one is going to be minus e to the power minus x2, right? And times the derivative of the power, which is 2x. So you will have the 2x e to the power e to the minus x squared, and by putting 0 you will see that it's going to be 0. It is not positive and it is not negative, therefore you don't have any information, which we talked about, that in this situation you should kind of draw it, or you can put the numbers before and after that, which actually you see that f of minus 1 and f of 1, both of them in the main function is equal to 1 minus e to the power minus 1, which is always positive because 1 is bigger than e to the power minus 1. Therefore, before the fixed point and after the fixed point, both of them is positive, which Anna last session said it absolutely right, that in this session you have a kind of semi-stable, or better to say half a stable. Half of it is stable and half of it is unstable. And you can also talk about this type of example, which is a nonlinear one, r minus x2. Why it is nonlinear? Because it is not first power, it is x squared. And again, you put the x dot equal to 0 and you find that x2, x squared is equal to r. And now it will be important, and we will work on this, which depends on the value of r. Because if r is negative, then both fixed points are complex and we don't deal with that now. If r is 0, then we have a fixed point at x, because x2 is equal to 0. And if it is positive, then we have two fixed points, square root of r and minus the square root of r. And again, for finding the derivative of it, actually it is written the second derivative, but it means actually, because it is x dot, so it's not the second derivative exactly. It's the first derivative of x dot, so which is equal to f of x. So f prime of 0 is equal to 0 again, and in this fixed point, and for the other, like the other two fixed points, which are the square root of r and minus square root of r, is equal to these values, which depends on the sign of f prime, because if the sign of f prime is negative, therefore it is stable, otherwise it is unstable. So if you don't have any question now, we can talk about bifurcation. Do you have my screen? I have some, but what makes fixed points stable? Like, why are negative slopes considered stable and positive one unstable? I see. Yeah. Okay. Okay. So let me actually tell you this. It's a good question. So here we can see. So why we call it stable and why we call it unstable? So when x dot is equal to 0, we know that this is the representation, this is the point of fixed point. So x dot with respect to x, we have a graph like this. Therefore, this, and this, they are fixed points. So now we want to know whether they are stable or not. So if we draw the slope of x dot, the slope of this graph, it is negative. What does a slope mean? A slope means the first derivative of x dot. So if it is minus, we call it a stable. Why? Because before this point, which is this part, x dot is positive, right? Here you can see that x dot is positive. What does x dot positive mean? Like take it, it means that x is increasing. So therefore, if I have a point, if I have a state here, it is increasing. Like the x of it is increasing. And if the x dot is negative here, then x is decreasing. Therefore, it is going toward left. So if it is positive, it goes toward this point, this fixed point, and if it is negative, the state of the system, the x is going through toward this fixed point. Therefore, and repelling from this one. And this is why we call it stable, because if you take the state of this system, for instance, put it here, then it refers back to the fixed point. If you take it here, then it refers back to this fixed point. Therefore, we call it stable. If you do a perturbation, it comes back to its equilibrium state. However, on the other hand, if you have an unstable fixed point, like this one, which the slope of it is positive, which f prime actually is positive, then you can see that if you have a point like here, like in the origin, in the origin x dot is positive. Therefore, the x is increasing. You can follow this arrow. Therefore, it repels from this fixed point. And if it is in this side, because x dot is negative, therefore it is going to repel from, like, away from this point. And this is why we call it unstable. With a little perturbation, you see that it goes through toward this fixed point or this fixed point, and therefore we call it unstable. Is that clear? Okay. So you got it seems. That's good. So I just do a quick overview here. We talked about some mathematics, but those mathematics are not that much important. Just the basic idea is important. That if f prime is negative, then it is stable, the fixed point. If it is positive, then it is unstable. And so this is not important that much. We talked about this half stable fixed point, which is interesting in the idea of bifurcation. So for bifurcation, which is a parameter that changes qualitative structure of our system, it can have two things, like creating or destroying the fixed points or changing their stability. So for the first one, we talked about saddle node bifurcation, which in saddle node bifurcation, it has a very normal form like x dot equal to r plus x2. And if you see, like here, if you see that if r is negative, if you draw this graph, then you see that it is crossing the x dot equal to 0 two times. Therefore, you have two fixed points. If r is equal to 0, then x dot is equal to x2, x squared. Therefore, you just have one crossing here, one tangent intersection actually. And if r is positive, then you do not have any kind of intersection. So this is an interesting thing, that in saddle node bifurcation, you have two fixed points. One of them is stable, the other one is unstable. And in the bifurcation point, they are going, like, reaching each other, colliding each other, and annihilating each other. And the fixed points are going to be destroyed. So this is the saddle node bifurcation. And the bifurcation diagram, which we also talked about, you can find by x dot is equal to 0 and draw, instead of x dot with respect to x, you draw x with respect to r, and you will see that a family or a set of stable fixed points you have for this part, like this blue line, and a family or set of unstable fixed points in this dashed blue line. And this is coming from the normal form. So the normal form is this, right? X dot is equal to r plus x2. So at fixed point, x dot is equal to 0. Therefore, r plus x star square is equal to 0. Therefore, x star is equal to plus and minus square root of minus r, which depends on the value of r. So you have a family of x stars which depend on the value of r. r minus, like positive 1, it's going to be like by the slope of it, it's going to be positive or negative, which tells you about the stability of it. So this is just an example, which we have it actually in our practice sheet, but this is just an example, and this is the saddle node bifurcation. If you don't have a question, which, okay, so it's stable if the growth rate becomes negative and the entity starts reducing. So when you are talking about growth rate, it means that you have a coefficient about the variable like x. So if you have something like r, if you have something like rx, like here in the logistic equation, if you have something like rx, then this r means the growth factor. But in that one, I'm not sure you can call it growth rate. You call it like a control parameter. So if it is as well, if the growth rate becomes negative, it depends on your equation, because it depends on your equation. If your equation, for instance, here, yes, here you are right. Here, with this saddle node bifurcation that has this normal form, it depends on r, yes. But we are going to talk about other types of bifurcations, and it's not going to be like this anymore. It depends. I am going to answer your question. Any more questions? No questions. Okay. Okay, so the second type of bifurcation, we are talking about 1D systems. We are talking about one-dimensional systems. And the important thing about one-dimensional, because in the normal way we didn't talk about bifurcation, and it was so much boring. We had fixed points and or growth. That was all, or decay. But if we have a kind of bifurcation, then the situation is going to be interesting. So the first one was saddle node bifurcation, and the second one is transcritical bifurcation. Its name is transcritical. So in saddle node bifurcation, we had fixed points that are going to be created or destroyed, but here we are talking about the stability of the fixed points. In transcritical bifurcation, the stability of the fixed points are changing. So a fixed point exists for all values of the parameter. Like for instance, take a parameter like the injected current, for instance. If the fixed point never be destroyed, and for all values we have a fixed point, then we have transcritical bifurcation. However, its fixed point is going to change in stability. The stability of its fixed point is changing as the parameter is varied. So the normal form of it is x dot equal to rx minus x squared. So you can see that in saddle node bifurcation, x dot was equal to r minus or plus x squared. This sign is not that much important. You see, let me actually show you here. Here in saddle node bifurcation, you have r plus x2. But here you have rx minus x2 or plus x2. You have this x here. So this is very like an example of it is the logistic equation that we talked about, which was x dot equal to rx times 1 minus x over k, which you can say that rx minus rx2 over k, right? So this is the normal form of it. Let me check whether you have no question. Okay, so we have x dot equal to this was the normal form, right? So I factor the x, and then x dot is going to be x times r minus x, this red part here. So I'm interested to find fixed point again. What is fixed point? Fixed point is going that it is saying that the point is fixed. There is no change in x. Therefore, x dot is equal to 0. Then you can find the fixed point. So if x dot is equal to 0, then x is equal to 0 or x is equal to r. Therefore, this x star is equal to 0 or x star is equal to r are the two values that are my fixed points. Therefore, I show them with this star, like x star. And the point here is this. You see, this is transcritical bifurcation. And in this transcritical bifurcation, we told you that actually for all values, a fixed point never be destroyed. Therefore, this x star is equal to 0. It is indestructible. It means that always for all values of r, which is going to be our bifurcation parameter, for all values of r, x star is equal to 0 is your fixed point. But why? Because in the normal form you have x r x, but in the saddle node bifurcation it doesn't happen. This is why it depends sometimes, a lot of times it depends on r. But here you have a fixed point that does not depend on the parameter. So this is how you can find the fixed point. So now we are interested in stability of it. For stability, we take the derivative of it. What is the derivative of it? F prime of x is equal to d over, let me actually check whether you have a question. No. So f prime of x is equal to d over dx of this formula over here, which is rx minus x2, which the first one, r does not depend on on x, therefore you don't have any change, and d over dx of x is equal to 1, therefore this the first derivative of the first part is r, and the first derivative of the second part is taking this power like as a multiplication of it, and it's going to be minus 2 times x, right? So f prime of x is equal to r minus 2x. And you have two fixed points. You have 0 and you have r. So what is f prime of the first fixed point? It is going to, like you just put the x over here, and f prime of 0 is equal to r, right? And f prime of the second one, which is r, is equal to r minus 2r, which is minus r. So this is the thing that actually Hunaid, if I am saying it right, sorry if I am pronouncing it wrongly. So this is the thing, that it depends on the value here. Like if r is positive in this form, the fixed point is unstable because f prime is positive. And if r is negative, the f prime of that fixed point is negative, therefore it is stable. However, the other fixed point, f prime of it is negative if r is positive, therefore it is stable. And if r is negative, then f prime is positive, therefore it is unstable. So if we want to draw this, we can say that we have x dot with respect to x over here. All of them are x dot with respect to x. So in general, we have this y equal to minus x squared, something like this, right? We have this. So we have this sketch in our mind. Therefore, we say that if r is negative, what if r is negative? R is negative, therefore here it is going to be like, where is the for here? X dot is equal to rx minus x2. So you have an rx. So if r is negative, then you have a kind of shift through the left. If r is 0, then you don't have anything, and it's exactly like minus x2. And if r is positive, you see that there is a shift through right and up and up. If you draw it by Python or like exactly here, you can understand it, because if x, for instance, is positive and r is also positive, like here x is positive and r is also positive, therefore you have a positive term for x dot. Therefore, if you draw this minus x2, which is this, if you add a positive form, you will see this shift through the right and upward. And again, with the same logic, this part x dot is positive, therefore these points, these are the two fixed points, right? Because x dot is equal to 0, and again here it is positive, and it is repelling because x is increasing, and here x dot is negative, therefore x is decreasing, and it is attracting through this stable fixed point and repelling from this unstable fixed point. And here you again have the bifurcation thing, the bifurcation idea, which it is half stable. And for the positive r, you can exactly see the logic as well. So you see that if now I have a negative r, right? With increasing r, so I am increasing r, then this unstable fixed point is approaching through this origin, and you will see that they are kind of colliding, and then like in saddle node we had this collision and destruction of the fixed points, but here you just see the change in stability. Like the origin here in r minus, it is stable, and here it is an unstable fixed point. Therefore origin has become unstable by increasing the r, which is the parameter. So you do not have any destruction of the fixed points, but you have the change in stability of it. This is why people call it exchange of stability between two fixed points. You can see here, right? Unstable, stable, and here you can see stable, unstable, like the origin changed its stability. So the saddle node bifurcation, in it fixed points are created or destroyed and disappears. But in transcritical bifurcation, fixed points are switching the stability. And now I want to talk about bifurcation diagram. I just check whether you have a question. Okay. So in the bifurcation diagram, we are interested in graph of x with respect to r. So we have two things. We have x is equal to 0 and x is equal to r. Why? Because they are the two sets of our bifurcation. So x is equal to 0 is this line, and x is equal to r is this line, right? And you see that here actually, so you see that here for this is r, right? The horizontal axis is r. So for the negative parts of r, we had this family of fixed points which are stable. This is the continue of it, which is going to be unstable. This is actually here, right? Because the origin here was stable, and now then at this point, which is half stable, it is going to be unstable. So the family of fixed points are changing their stability. And here again you can see that the other fixed point, which is for r negatives, which was unstable, then it is going to be stable for positive r's by increasing r. And again you can see that this family from unstable is going to be stable. And these yellow things, they are just the flow that if the state of your system is here, for instance, if you just release it, then it absorbs to these stable fixed points, and it is repelling from unstable fixed points, and repelling from unstable fixed points, and absorbing to stable fixed points. What it means that this family of fixed points, this set of fixed points, are colliding with this family of fixed points, and they exchange their stability. The stable one is going to be unstable, and the unstable one is going to be stable. For negative r and for positive r's. So this is the idea, and Sorry for this, I don't know what happened. So if you just want to draw this diagram, for instance, you can see that you again have the NumPy library and Matplotlib library, and you have a range for positive r's, which I just said it starts from 0 to 100, and for negative r it starts from minus 100 until 0 with the steps of 0.1, and this is just x is equal to 0, and for this I have a function like xrp, which is exactly rp, right? This is very simple, like y is equal to x, as well as for the negative one, like I have a function like x of negative r's, which is equal to negative r's, and I just plot them based on the blue lines for stable ones and the dashed line, the red dashed for the unstable ones. And if I don't think actually it works. No, it doesn't work. I should write again because I run it once. And so you can see that you can draw these things very easily, right? This is the x equal to 0, and this is the x equal to r, and this is the stable fixed point, the family of them. This is the unstable fixed points, the family of them. And for these classifications, you use those very simple analytical things, which is finding fixed points based on x dot equal to 0, as well as its stability based on the first derivative of x dot. And you can find that here this one is unstable and it's going to be stable. That's all. No questions, right? It seems right. Okay, so now we want to talk about the third one. This is the last one. The last one is the pitchfork bifurcation. The pitchfork bifurcation, its name, we talk about it because its bifurcation diagram is kind of it's like pitchfork, and this is just a name. So this kind of bifurcation occurs in the system with symmetry. And for just having an idea of this symmetry, is that you have a weight on a beam over here, and by increasing the weight, then after a threshold you see that this beam is going to bend, right? So here the beam is stable, and if load exceeds, then the vertical position has gone to be unstable. This is, and it goes to the left or to the right. You have a kind of symmetry of spatio left and right symmetry. So then after that you have this weight is going to be here or here, and you have two stable fixed points, right? Whether it is in the right side or whether it is in the left side. So this pitchfork bifurcation has several kinds, but we talked about two main of them. One of them is supercritical pitchfork bifurcation. So you see that all of them is coming from this differential equation form. In saddle node we just had r minus or plus x2. In transcritical we had rx minus or plus x2, and now we have rx minus x cubed. This is the normal form of supercritical pitchfork. And by symmetry we mean that if we replace x with minus x, then what will happen? We have this x dot. What is x dot? X dot is dx over dt, right? So if we replace x with minus x, then you see that d over dt of minus x is going to be equal to minus r times x, which is this. I just replaced x with minus x, and this minus is coming from that minus x squared. Actually, I should take this square, this cube out of this parenthesis. It's a kind of mistake. It's not wrong, but it was better to be outside of this parenthesis. So then this minus is coming out of this derivative, and then again you have minus x dot equal to minus rx minus minus x cubed, and you can cancel out these minuses, and again you have the normal form x dot. They are equal. X dot equal to rx minus x cubed. So you have a kind of left-right symmetry. If you replace x with minus x, still the normal form is same. This is why we say that the equation is invariant with this replacement, and this brings the idea and understanding and modeling of symmetry in the models that you have symmetry. Okay, let me check whether there's a question. Plus x cubed. This is a good question actually. This is a very good question, because this minus x cubed here we have plus x cubed, and this is another type of pitchfork bifurcation. This is the second form. So it's an interesting thing actually, which soon we talk about. Okay, so again we have this x dot equal to rx minus x cubed, and we factor the x, and we have this formula x times r minus x squared, which we want to find the x point, the fixed points again. So we put x dot equal to 0, therefore x star is equal to 0 is one of our fixed points, as well as this r minus x2, x squared, it is going to be 0, therefore x squared is going to be equal to minus r, and therefore x star can be positive and negative of square root of r. So we have three fixed points based on the sign of r, because r is under square root, therefore r should be positive, and these two solutions are only valid for positive r, right? And okay, so and then we say that I am just trying to talk like slowly, and if you think that it's better to talk faster, tell me. So f prime is equal to the first derivative of this x dot with respect to x. So the first one is going to be r, rx will be r, and minus x cubed is minus 3x squared. Therefore, we in this fixed point of x star equal to 0, we have f prime of 0 equal to r, because x is 0 here, and you can forget about this part. And f prime in instead of 0 in the other two fixed points, which is valid for positive r's, we have r minus 3 times square root of r squared, therefore minus 3r. It is going to be minus 2r, which now we have these f prime, right? We have f prime at the first fixed points, and as well as f prime in the other two fixed points. So in the first one, for if r is negative, then again f prime is negative, therefore it is stable. And if r is positive, then f prime is positive and it is unstable. And if we draw x dot with respect to x for negative r's, we see this. And again, you can see that before this point here x dot is positive, therefore any state here is going toward the origin, which means x is increasing, and here x dot is negative because it's in the negative axis of it, right? Therefore it is going toward the origin again, therefore we call it stable fixed point. And if r is equal to 0, again you have kind of same graph. However, when r is positive, you have this diagram. You have 3 points, 3 intersections. You see that here f prime is it depends on r, right? If r is positive, then minus 2r is negative, therefore it is stable. So for this and for this, you see that these are the square root of r and minus the square root of r. For x dot, they are positive and the origin is unstable. It's the important part of it, that this stable one is changing its stability, and two new fixed points is bifurcating out of this stability of the origin, which is coming from that symmetrical idea, which we call it symmetrical pairs. So it's maybe it's a good, quite cool recap, maybe, that in saddle node we didn't have any fixed point, and then we had one fixed point, and then we had two fixed points, or vice versa. We had two, and then we had kind of half a stable and just one fixed point, and then it destroyed. However, in transcritical bifurcation, we had two fixed points, and then it changed to one fixed point, and again to two fixed points. But here in pitchfork bifurcation, we have one stable fixed point, and then when r is equal to 0, which is the moment of bifurcation, it is still 1, and then we have 3. This is an interesting situation, and this type is going to be called supercritical. That actually this supercritical means that the bifurcation solutions are stable. And let me check here. No questions. Okay, so now we want to again draw this this diagram, right? So the bifurcation diagram. So for finding fixed points, we used x dot with respect to x, but for bifurcation diagrams, we use x with respect to r, the parameter. Like in Hodgkin-Huxley, it is I, the current. So drawing x with respect to r, we have two lines again, right? We have one of them is x is equal to 0. The other one is x is equal to square root of r. And we see that one stable fixed point here for negative r's, we have one stable fixed point. And then for positive r's, we see that this stable fixed point is going to be unstable, and two stable fixed points are generating, are bifurcating out of that stability. So this line, this family of fixed points here, which is stable, it is going to be unstable. And then we have two sets of fixed points which are stable. And you see that this picture is like pitchfork, and this is why we call it pitchfork bifurcation. So for this negative r, we just have this line which is stable, and the flow of any kind of state here, you see that it is going to absorb and attract to this stable fixed points, family of fixed points, and here as well, but it is repelling from this unstable one. Therefore, you see a kind of symmetrical thing here, right? If we do not have this unstable fixed point, a state here, it doesn't know that it should goes to this stable fixed point or this stable fixed point. But because we have this unstable fixed point, we have a repelling force here that helps the, actually they are completing each other. This unstable line and this stable set, like parabola, they are completing each other. Any kind of system here, it absorbs to this stable family of fixed points, and here as well. So this was the supercritical, and now we want to talk about subcritical. Any question? Sorry, I need to bring a glass of water. I just come back in 30 seconds. So sorry for this time. The best drink in the world is water. So we want to talk about subcritical pitch bifurcation. As Hunayt mentioned, it's this time the sign is positive, and we have in the normal form x dot equal to rx plus. Wait, actually, before that, I just this one is also cool. Just this is just if you have the idea that how to draw the things, it helps, right? So again, you have this library NumPy and Matplotlib, and for the positive r's and negative r's, you have this range, and you have x0, and for x for the positive parts, you have the square root of positive r, right? Here, sorry for this. Here you have x star is equal to positive r, and x star is equal to minus square root of r, positive like square root of r, and negative square root of r. Therefore, you see that you can define this function like this. SQRT is like a square root of RP, and yeah, and if you just again draw these things, actually I should draw these things. So this is the positive one, which is stable, and this is the negative of that, negative square root of it, which is again stable. And for the other one, like for negative r, x0 is again stable. So here you have this another stable, and for the positive r's, that x0 is going to be negative, right? Going to be unstable. So yeah, that's how we can just see. You see that it's a kind of pitchfork that for positive r's, you can see that you have two sets of stable ones and one set of unstable one. Okay, let's talk about subcritical pitch bifurcation. Let me check here as well. No. So the normal form is going to be x dot equal to rx plus x cubed. So the difference with supercritical is the sign of cubic term. Instead of minus, now you have positive or plus. So in supercritical you have minus x cubed. In subcritical you have positive x cubed. The idea is that this cubic term is stabilizing, but in subcritical it is destabilizing that family of fixed points. You can see it in the bifurcation diagram. So again you have this x dot is equal to rx plus x cubed, and you factorize the x times r plus x2, and if you just put it equal to 0, then one of the fixed points is again x star is equal to 0, and the other one is that this term should be equal to 0, which means that x2 is equal to 0 to minus r, which means that x is equal to positive and negative of square root of minus r. And so these are our fixed points, right? And here you want to talk about its stability. So f prime of x, this is our f of x, and this is our f prime of x, is going to be the first derivative of the first term and the first derivative of the second term, which I'm sure you know how to calculate this. And f prime of 0 will be now this is one of the fixed point, and this is the other fixed point, the other two fixed points, right? So in this fixed point, f prime of 0 is equal to r plus 3 times 0, which is r. And if it is positive, then f prime is positive. Therefore, for positive values of r, you have unstable fixed points. And if it is negative, then it is unstable, and f prime is negative as well, and it is unstable. However, here, if you want to calculate the f prime of these family of fixed points, positive and negative of square root of minus r, it is going to be r here, like here, r plus 3 times positive and negative square root of minus r squared. So this positive and negative are vanishing because of this square root, and this square because of this power, and this square root is also vanishes, and you will have r minus 3r, which is minus 2r. And if r is negative, then for this you have this f prime is positive, which means that it is unstable. I mean, if r is negative, then this minus makes this whole formula like f prime positive, therefore it is unstable. And it doesn't make sense to talk about our positives, because it is under this square root and it is going to be imaginary. We can talk about it, but here we are working in real space now, and we just talk about negative r's. And again, if you draw the graphs, you can see that the origin is positive for r minus. Why? Because here this graph has negative values over here for x dot, negative values over positive values over here for x dot, and therefore you see that there's an attraction through origin and repelling from these 2 points. So you have unstable, stable, and unstable, and by increasing r, it is going to be 3 fixed points are going to be like just one unstable fixed point, and these 2 are just they are just different in the slope of touching this origin, but basically they are kind of same. So again, with this, if you again draw the pitchfork, if you again draw the bifurcation diagram, you can see that a family of stable fixed points are going to be unstable, which is corresponding to this in origin. You see that it is going to be unstable, and these 2 unstable fixed points, which is corresponding to these 2 parabolic shapes, are unstable, and after r0 they don't exist anymore. So again, if you have a kind of flow of like, if you have a state, if you have a state of system over here, the flow of that state is repelling, is going to be repelled far away from these unstable sets of fixed points and going to be absorbed to this stable one. And that's it. So the bifurcation in 1D here is finished. So let me see. System F is stable if F prime is less than 0. Is this a statement correct? System F is stable. F prime is less than 0. Yes. Well, yes, yeah. Well, the system F is equal to x dot, right? So you have the normal form like x dot equal to f of x. With that notation, yes, that's correct. In that range, right? In that range, because f prime, we calculate this f prime for fixed points, right? In the fixed points, we calculate the f primes, and if f prime is less than 0, that fixed point of the family, the function f, it is stable. You're welcome. Uh, so if again, all we talked actually about bifurcation in the practice sheets now. If you have, if you want to, if your system has this kind of, this is Rx minus x2, right, which we talked about. For minus R and for positive R and stability of it, and we had these diagrams as well. And this is the transcritical bifurcation diagram. And for this Rx minus x cubed, we also talked about it, and the bifurcation diagram of this supercritical pitch bifurcation. And for this positive x cubed also we talked about it, and this subcritical pitch bifurcation. So if you, this is going to be, we can also talk about it, but I prefer to, because your mind is ready for something that we can talk now, I prefer to talk about an interesting paper. If you have a question, which you do not. Okay, so actually, maybe I can find it here. Yeah. So this is not, this is just for showing that how much it can be important. We have, because Anna actually asked last session, asked about cognition. So it's an important thing that to know that we are dealing with some neurons, and we are talking about the dynamics behind the neurons with changing with time, and we are not talking about the network of neurons yet. So this is an important thing, as well as you can also consider this, that it's a very big step to create cognitive behaviors out of network of spiking neurons. If you can really solve this problem, you solve a major, it's bigger than just winning a Nobel Prize. It's still these bridges are not fulfilled. We don't have these bridges between these levels of complexities. So, but the idea is that with this kind of reductionism perspective, because we have a kind of reductionism view, we say that we reduce the system to simple elements, and if we know the behavior of the simplest element of that system, and we know the way that if we know the configuration of them, how they are interacting with each other, then we can build a bigger picture. And then out of network of neurons with like spiking neurons, we can build other things like talking about memory, for instance, talking about attention, for instance. These kind of things, if you can really do that, and some people are getting closer to that, but it's a bigger step. So and also Hunaid asked about some papers, like if you are interested in. So I found this having this idea of how collective variables are important, and how much actually this dynamical system perspective is informative and powerful tool for classification, for classifying the behaviors of the system. So this paper is published by Kelso and Bressler, Cortical Coordination Dynamics and Cognition, which you can actually see that the lack of theoretical language for expressing cognitive functions in neural terms, because of this, they propose an approach to understand operational laws in cognition based on principal coordination dynamics. So they said that it has been unclear whether a single unifying perspective exists. So this is actually kind of close to binding problem. How can you take a unified picture out of interaction between neurons? So they say how for a given function, cognitive function, the nonlinear coupling among component parts gives rise to a wide variety of complex coordinated behaviors. Our approach is first to identify neural components that are appropriate to cognitive function, and then investigate the ways in which those components change their relations in time. We focus on cerebral cortex. So, because it is at this level that cortical pathways, both within the cortex and with subcortical structures, are organized. Our goal is to address the critical question of how interaction among the large number of anatomically distinct cortical areas give rise to the emergence of cognitive function in real time. The coordination dynamic of a complex system refers to the manner in which state of interdependency among the parts change with time. These principles derive from concept of self-organization and pattern formation that use the language of coupled nonlinear dynamics to describe how patterns of coordination arise and evolve in time. So they came with this idea. They said now you can understand easily these kinds of modelings. They said that we have a formula like this. Phi dot is equal to delta omega minus a sine of phi minus 2b sine of 2 phi plus square root of q eta. So, or epsilon, whatever, delta. This is just the noise, and this is just the strength of noise, and you don't need to conceptually worry about it. But here you can see that here A and B are the coupled parameters. Again, you can see that we have two parameters, which bifurcation and the state space soon is going to be emerged out of it. So you have one variable like phi, and you are interested in the change of phi with respect to time, this where can I find it? Here. The simplest dynamics occurs. This delta W represents intrinsic frequency difference between the uncoupled components. It means that actually we have this. What is this phi? This phi. Let me actually talk about this variable phi. We call it like collective variable phi. We have a collective variable phi, which is going to you are going to understand the behavior which is coming from like the collective behavior of your system. The relative phase means like again you can see an understanding between
the screen is frozen.
Sorry.
The screen is frozen. We can see a certain diagram, but
Ah,
not the paper you're talking about.
really? You don't have my screen? Okay, let me again do this. Oh, sorry, guys. Okay. Now you can see. Sorry. I talked a lot, and okay. So we have 5 minutes, and I try to just give you the idea. Uh, Okay, now you have my paper, right? Now you can see the paper. May one of you talk, like unmute and talk, just saying yes.
So I can't see the paper. I just see the screen of the meeting.
I see why it happens like this. Can share a URL to the paper. Yeah, I will share the URL of the paper now, maybe, because I have downloaded it, and so just I don't know how can you actually find this, uh, because maybe it's not achievable. And okay, by the way, this paper takes a bit time. Maybe we can talk about it next time, because we cannot finish it in this short time. Yeah, if you also, because also you don't have my screen, so maybe you can download it and next time we talk about it. Ah, now you can see it. Okay, still you can see it, right? Because I just don't want to change the screen to the meeting screen. You don't have it. Okay, okay. Next time we talk about it. I think it makes sense because we cannot do it like this much fast. Okay, I disconnect the I don't share the screen anymore. So we almost finished in, like, by time. It passed very soon. Do you have any question regarding the topics or the thing you talked about? The paperwork or the evaluation process with Professor Pipa. Yes, Huna. Yes, it is. It is kind of illegal. You can't find it, right? Yeah, I mean, so about evaluation process or paperwork or stuff, you talked about it with Professor Pipa last week, and what was the result? If Because I didn't participate, and I talked about it with Professor Pipa, but I just want to know your opinion as well. Okay, in group of three, right? Okay, okay, okay. I see. So, I mean, it's for all of us, it is so much important that you work on the things that you are interested in. If if you are interested in some basic ideas or some neural models or some like this one, like collective variables or a lot of other stuff. Uh, we can also later, because we will talk about synchronization and these kind of things. They are interesting. So, I mean, it depends on your ideas, and I am, I, we are all trying to work on our interests. So, yeah, that's the best thing if you can work on the thing that you really like. And I will try to introduce some papers as well. If you want, you can choose and work. Otherwise, you can take your own or whatever. Okay. So it was great to hear you again. It was, and I hope it's a rainy day, but I hope you enjoy. By the way, the rest of the time of today. Thank you. So see you next week again, and feel free to send me emails and ask your questions. Goodbye. Ciao.